Roughly 13.8 billion years ago, everything that exists, every galaxy, every star, every atom in your body, and space itself, did not exist yet. Then, in an event physicists call the Big Bang, it began. This is not, despite the popular image, an explosion happening at some specific point inside an already existing empty space. It was the beginning of space and time themselves, expanding outward from an initial state of unimaginable density and temperature. Meaning there is no outside the Big Bang expanded into, because outside, in any ordinary sense, did not yet exist. We know the universe had a beginning, rather than existing forever unchanged, largely because of a discovery made in the 1920s. Astronomer Edwin Hubble found that distant galaxies are moving away from us, and the farther away a galaxy is, the faster it appears to be receding. Run that observation backward in time, and it points to a single conclusion. Everything was once far closer together, and expanding from a common origin. This is the story of that origin, the first moments of everything pieced together not through guesswork, but through some of the most rigorously tested science that exists. The single strongest piece of direct evidence for the Big Bang was discovered almost by accident, by two radio engineers who were not even looking for it. In 1964, Arno Penzias and Robert Wilson, working with a sensitive radio antenna in New Jersey, kept detecting a faint, uniform background hiss they could not eliminate no matter what equipment adjustments they tried, even after ruling out pigeon droppings on the antenna as a serious possible culprit. Physicists elsewhere had actually predicted, on theoretical grounds, that exactly this kind of faint radiation should exist if the Big Bang theory was correct. Leftover heat from the early universe, cooled by billions of years of cosmic expansion into faint microwave radiation, arriving uniformly from every direction in the sky. This cosmic microwave background, as it's now called, is essentially a photograph of the universe as it existed just under 400,000 years after the Big Bang, the earliest possible moment light itself could travel freely, because before that point, the universe was so hot and dense that light constantly scattered off free-floating charged particles, unable to travel in a straight line at all. Satellite missions since, including NASA's COBE and WMAP spacecraft, have mapped this afterglow across the entire sky in extraordinary detail, revealing tiny temperature variations, differences of only millionths of a degree, that mark the seeds of every galaxy that would eventually form. Penzias and Wilson received the Nobel Prize for what began as an annoying, unexplained hiss in their equipment. If the cosmic microwave background is a snapshot from roughly 400,000 years after the beginning, physicists have also worked out, through both theory and observation, what happened far earlier still, within the very first seconds and minutes. In the earliest fractions of a second, the universe was almost inconceivably hot and dense, and physicists studying particle physics believe the four fundamental forces we recognize today, gravity, electromagnetism, and the two nuclear forces, may have originally existed as a single unified force, only gradually separating as the universe cooled through its first fractions of a second, a process actively studied using data from particle accelerators like the Large Hadron Collider. Within the first few minutes, the universe had cooled enough for a process called Big Bang nucleosynthesis. Protons and neutrons fusing together to form the very first atomic nuclei, primarily hydrogen and helium, along with trace amounts of lithium. This is precisely why the universe today is overwhelmingly made of hydrogen and helium, and the predicted ratio between them, calculated from Big Bang physics, matches what astronomers actually observe in the oldest, most pristine gas clouds with remarkable precision, one of the theory's most successful, rigorously tested predictions. Everything heavier than these lightest elements, the carbon, oxygen, and iron that make complex chemistry and life possible, came later, forged inside stars, exactly as we've covered elsewhere on this channel. The Big Bang built the raw ingredients. Stars did the rest of the cooking. Studying the Big Bang in detail has repeatedly forced physicists to confront how much about the universe remains unexplained, even within an otherwise remarkably successful theory. One major puzzle is called the flatness and horizon problem. Regions of the universe that, given the known speed of light and the universe's age, should never have been in contact with each other, nevertheless show nearly identical temperatures and properties in the cosmic microwave background. The leading explanation, called cosmic inflation, proposes that the universe underwent an incomprehensibly rapid burst of expansion in a tiny fraction of its first second, far faster than the speed of light applies to ordinary objects moving through space, because space itself was doing the stretching. This would explain the uniformity by pushing regions that started out in contact far apart, faster than light could otherwise connect them again. Inflation remains an active, still developing area of research. It explains several otherwise puzzling observations elegantly, but the exact physical mechanism driving it is not yet fully settled, and physicists continue searching for more direct observational evidence. And as we covered when discussing dark matter, roughly 95% of the universe's total content consists of dark matter and dark energy, components whose gravitational and expansive effects we can measure precisely, but whose fundamental nature remains one of the biggest open questions in all of physics. The Big Bang Theory tells us how the universe evolved in remarkable, tested detail. It does not yet tell us fully what most of that universe is actually made of. Put together, the evidence for the Big Bang is among the most thoroughly cross-checked in all of science. The recession of distant galaxies, the cosmic microwave background's precise temperature and pattern, and the measured abundance of light elements all independently point to the same origin story, each discovered through entirely different methods, decades apart, by different research teams who were not looking to confirm each other. That does not mean every question is answered. What triggered the Big Bang itself, what, if anything, came before it, and whether that question is even physically meaningful given that time itself may have begun at that moment, remain genuinely open, and in some cases may lie permanently beyond what observation can ever test directly. What we can say with real confidence is this: 13.8 billion years ago, in a state we still do not fully understand, the universe began expanding from an incomprehensibly hot, dense origin. It cooked the first atoms within minutes, cooled enough for light to travel freely within 400,000 years, and spent billions of years afterward building galaxies, stars, planets, and eventually, on at least one small world orbiting one ordinary star, something that could look back at the sky and reconstruct its own beginning using nothing but starlight and careful measurement. Every atom in your body took part in that first second. You are not simply observing the universe's origin story from the outside. You are, quite literally, still made of it. If this story moved you, subscribe to Cosmic Horizons. The universe is full of stories like this one, and we tell a new one every day.